Hi everyone, it's Laura from Lanterna Education, and today I'm bringing you another video on IB psychology. So what we're going to look at today is another part of the biological approach to psychology. So if you've watched one of my other videos on the biological approach, you'll know that we split IB psychology into three kind of main approaches to psychology. So we have the biological, the cognitive, and the sociocultural, and today we're going to keep going with the biological. So specifically what we're going to look at today is neuroplasticity. So this is something that people sometimes struggle a bit with because it's a bit of a weird concept. But again, since it's biological, what we're really concerned with is we're looking at specifically how our brain's patterns of activity essentially relate to our actual behaviors and attitudes and so on. So what neuroplasticity actually is it's the ability of our brains to change their structure based on the environmental conditions. And so that sounds more complex than it is, but really what it means is that we don't have a fixed brain. We're not born with a brain that then stays exactly as it is for the rest of our lives. That's not at all the case. Instead, we're born with a brain, and that brain is then susceptible to changes based on different stimuli that it might then encounter. So for example, we might learn a new skill, and then our brain would register that new skill and basically form a new pathway that facilitates that, so it makes it easier for us to do. That's how we form habits, that's how we learn new things, new skills, everything like that is all because of our brain's neuroplasticity. So it's a lifelong ability, which essentially means that we can keep learning forever and our brain will change as a result of it. So we basically keep developing and strengthening essentially some neural pathways based on these new experiences we have. So let's say that we learn to ride a bike, then our brain would quite quickly create a neural pathway which strengthens the connections in our brain that tell our hands how to hold onto the bike and tell our legs how to pedal and how to keep our balance, etc. All of that, all of the neural pathways and connections that are involved in learning that skill will basically strengthen. And so what we mean by that is basically by practicing something, that skill gets stronger. And that's specifically what's on the slide called dendritic branching. So you might have seen the layout of a neuron before. So a neuron essentially has many different parts to it, and it's really just a fancy word for a really long cell that's to do with neurotransmission. So basically at the start of the cell, there's these dendrites that branch out from it. And what dendrites do is they pick up messages from other neurons around that neuron. So if it receives a message from a different neuron, then it passes it on along the whole neuron, and that's a whole process that we don't need to go into. You don't need to know that. But what these dendrites are responsible for are forming those connections. So they're the branches that connect one neuron to another neuron and so on. So it can be a whole chain. So what dendritic branching does, or how it's involved in learning skills, is that the more that you learn a certain skill, the more these neural connections are kind of strengthened. So they're almost like, it becomes quite literally more of a habit because it's happening again and again and again. So our body, or our brain really, learns exactly how to do that without having any delay. So it becomes second nature, and that's really how that happens. And the other example of neuroplasticity that we'll talk about is cortical remapping. So similar to dendritic branching, it's also demonstrating neuroplasticity because it's the ability of our brain to, instead of forming these new connections, it's about reallocating a whole function. And what we mean by that is, for example, if you suffer an injury to a part of your brain, then you can actually reallocate, not intentionally, this is something our brains do all by themselves, but we can reallocate a function that's lost from that section to a healthy different part of the brain. So if, for example, you suffer a brain lesion, so like an injury in your brain, then that region which was damaged might transfer its function to a different region that is able to take over. So we'll look at both these in a little more detail by looking at studies which back them up. So to begin with, we'll look at a study by Tierney et al. And basically what this study is it was a case study of a 37-year-old man who was called M.A., and he suffered a lesion to his left frontal lobe as a child. And within the left frontal lobe is a region called the Broca's area, which I've spoken about before in a previous video. And Broca's area, if you remember, is involved in speech production. So actually producing the word. So it's not about comprehending things so much, it's about actually the physical, like your mouth moving, producing the words that you're wanting to say. However, even though he suffered this lesion, he for some reason was still able to speak, which is a huge question mark for all the doctors who examined him. And what they kind of realized after some time is that both of his parents, MA's parents, were deaf. So he grew up speaking, but he could also sign. And that might seem irrelevant right now, but once we go through this a little more, you'll see where that comes in. So he was able to sign, but he could also speak. So MA was then compared to 12 controls, so participants who were just used as kind of like a comparison really to MA. So just typical individuals who were all fluent in sign language and also verbally fluent. So like him, but without this brain injury. And what they did is they used PET scans, which is a functional scan. So you can see what's happening in the brain kind of like live. So as it's happening, you can ask someone to do something, perform an action, and you can see exactly how the brain responds as you're performing that action. And they tested both speaking and motor control skills. So let's take a look at what happened. So what they found was that MA's motor skills area actually lit up when he was speaking. So what that means is that compared to the control group, where the Broca's area lit up when they were speaking, as it should in normal individuals, then in MA, he'd somehow cortically remapped, so like reallocated this function to a different part of the brain, so to the motor skills area instead of Broca's area. So he'd managed to move the whole function, which meant that he still retained the ability to speak, even though he didn't have that speech center anymore. So it's really crazy, but that's exactly how it worked. However, what they then found is that the motor control skills of MA had worsened or were relatively worse than the controls. And that's because some areas of that motor control area had been replaced by the speech. So naturally, his function there was slightly impaired, but it meant that he'd been able to hold on to his speaking ability. So what we can conclude from this is that cortical remapping had essentially allowed a whole function to be moved, reallocated to a new location such that MA could still speak. And that's why the motor control skills area was probably used, is because since he was used to signing, he probably used his hands a lot in what his brain perceived as speaking. So that's why it was quite a natural shift for where the brain would send it. It tries to send the new function to somewhere logical. It can't just randomly create a whole new function in a brain part that's never seen anything like it before. So because motor control skills was linked to language production in MA, he was then able to move that function to that region. However, bear in mind what we said in the last video as well, is that this is just a case study. It's just one person we're looking at who had this abnormality, so we can't make any definitive conclusions, but we can use it as an example of cortical remapping and that it is possible. Okay, great. So the next study we're going to take a look at is by Dragonski et al. There were 24 participants in this study, 21 males, 3 females. So just bear that in mind as well if you talk about this study, is that there is a gender bias. It is more males than females. But what they did is they split this group into 2 groups. So they had one group learn to juggle for 3 months. So they were trying to learn a 60-second routine. That was kind of their goal for these 3 months. And then they had a group who had no training. So they just went about their lives as normal. They weren't juggling. And then they used MRI scans to look at the brains of both of these groups. So they wanted to look at the brain area in the right hemisphere, which is concerned with visual detection, which is kind of the key area for juggling because you need to be able to visually perceive where the balls are in the air in order to catch them. So what they found was that before training, so they had MRI scans before the 3 months and after the 3 months. The ones before, both groups had relatively the same brain density. So when they were comparing them, everyone looked relatively equal. However, after the 3 months, where group 1 had learned to juggle and group 2 hadn't, then group 1 actually had a greater brain density. And then they took it a step further. So then they said, what happens if after a further 3 months, where no one practices at all, so both groups don't practice this time, what would happen then? So would group 1 still retain that ability to juggle, and therefore would they retain the neural connections that had been strengthened? And what they found was that that was probably the case. So there wasn't as big of a difference, so it was only slightly different, but they were still different, but just slightly similar, essentially. So there was less drastic of a difference as there was straight after the 3 months of juggling. But it shows that we still retain that ability, it just weakens slightly. So we have the neural pathways, so the dendritic connections or the dendrites between neurons, but they just might not be as strengthened if you're not upkeeping the skill. And that's kind of what we hear people say anyways, right? You've always been told to do Sudokus and things like that to basically practice your brain function, keep it alive. But it's the same premise really at the heart of it, which is that if you practice something, you strengthen that ability, but that you can lose it. It's the whole use it or lose it, which isn't strictly true, but it definitely will weaken if you're not upkeeping it. And the reason that this shows itself as brain density is essentially because if you're forming more dendritic connections, so if the branches are thickening or if there's forming new dendrites, then technically our brain mass will increase because we're increasing the neural matter, right? And so that's how we can use the study as evidence of neuroplasticity, because by learning a new skill, then we're increasing that mass. I hope that makes sense. Okay, and so we can use both these studies as an example. It's great to have both because the second study isn't a case study of just one individual who's had some accident. This is actually just learning a normal skill. So it's quite generalizable and applicable to a lot of people because we're always learning new skills. So that's why it's great to have both sides of the spectrum here in this case, that we have an injury, but also a typical brain example. So that's all we're going to cover today. That's all about neuroplasticity. I hope that makes more sense to you guys and that you learned something today. If you're interested in more tutoring, check out Lanterna's website and you can get one-on-one tutoring that can be tailored to you. And also feel free to check out a blog post on how to get a 45 from some of Lanterna's tutors. Great. Thank you very much, guys. See you next time.